Hi, it's Mr. Mac, and in this, our 12th in the series of math skills that you need, we'll be looking at right-angled triangles and a theorem by an ancient Greek man by the name of Pythagoras.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
So this picture shows inside the square pyramid at the Louvre in Paris, France. We're learning to use Pythagoras theorem, and we'll be able to, by the end of this video, substitute two lengths into Pythagoras theorem to find the third side of various right-angled triangles. Just some background about pyramids. Here you see the square pyramid in front of the Louvre, and it's covered over by a black and white photo of the Louvre. Now, Pythagoras was a famous philosopher and mathematician who lived from about 570 BC to about 490 BC, which is about the time that the Persian Empire had conquered the Babylonian Empire and Daniel had been captured and was exiled with other Jews in Babylon. Pythagoras was born in ancient Greece on the island of Samos, which is just off the coast of modern-day Turkey. During a trip, because Pythagoras loved to travel, he liked to find out lots and lots of information from everywhere he went. He went to Egypt and he saw that the Egyptians used a very clever way to improve the stability of the ancient walls of the pyramids. And like this modern pyramid at the Louvre in Paris, the Egyptians built square pyramids. Now, the Egyptians used a rope with 12 knots tied evenly spaced around it. As you can see, I've got a bit of string here, and I've tied knots every 5 centimeters. And they made it into a loop like this, and when stretched out, it makes a right-angled triangle with the sides, the spaces between the knots as 3 on the right-hand side, 4 at the bottom, and 5 along the longest side. What happens then is that this triangle makes a right-angled triangle. And Pythagoras proved the theorem that the square of the hypotenuse of any right-angled triangle is the sum of the squares of the other two sides. So let's look at this 3, 4, 5 triangle. 3 squared, of course, is 9. 4 squared, 16. 5 squared, 25. And since 9 plus 16 equals 25, Pythagoras' theorem works for this right-angled triangle, but doesn't work for all triangles. Let's have a look. Here is a visual proof of Pythagoras' theorem, and let's see how it actually works with any right-angled triangle. So here's any right-angled triangle. I just happened to come up with this. We don't know the lengths of the sides, but we can label the shortest side as A, the next shortest side as B, and the longest side as C. In a right-angled triangle, we'll also call that the hypotenuse. Let's copy that and put it here on the side with A, B, and C, and copy it again, and copy it again. Now we have 4 right-angled triangles. And let's fill in the space. And the total area of the shaded part is a square, is C squared. Well, let's move one of the triangles down to here. Now, the area has not changed, even though it's a strange shape. So the total area of the shape is still C squared. Let's move this triangle down to here. And again, the total area of the shape is still C squared. Now, if you look on the left-hand side, and I'll cover this up, you can see that there is a square, and it's A times A the area of the square, the little square on the left, is a squared. And on the right-hand side, b times b, the area of the square on the right is b squared. So we now found that the total area of the shape equals a squared plus b squared. Therefore, c squared, the total area of the shape, must equal a squared plus b squared. And we've proven Pythagoras theorem. Well, let's use it. Let's find the hypotenuse. We're given a equals 20 metres, b equals 50 metres. We know from Pythagoras theorem that c squared equals a squared plus b squared. So let's substitute a equals 20, b equals 50. So we get c squared equals 20 squared plus 50 squared. 20 squared is 400. 50 squared is 2,500. Let's add them together and we get 2,900. To find c, we need to take the positive square root. We're dealing with distance, so we don't need to know the negatives. So the positive square root of 2,900 equals 53.85 and so on, which is 54 metres, correct to two significant figures. Well, what we can do finding a smaller side of a right-angled triangle. In this case, we're given the hypotenuse, c, equals 27 metres, and the shortest side, a, equals 11 metres. We know that c squared equals a squared plus b squared from Pythagoras theorem. So let's substitute. c is 27, a is 11. 27 squared is 729. 11 squared is 121. Let's rearrange and put b squared onto the left-hand side all by itself. So we make b squared the subject of the equation. So b squared equals 729 minus 121. Just check that you can do that yourself. To find b squared, we need to subtract 729 minus 121 is 608. To find b, we take the square root. Square root of 608 is 24.65. And rounded to the nearest two significant figures, we have b equals 25 metres. And so we've found the smaller side of a right-angled triangle using Pythagoras theorem. So we've seen how to use Pythagoras theorem in a couple of different ways to find out the length of either the short side of a right-angled triangle or the hypotenuse. In our next video, we'll have a look at some basic trigonometry. I'm Mr. Mac. Thanks for watching.